Welcome to the third step of Pi's journey. Today we shall continue delving into the topic. How did mathematics begin? Before fractions, negatives, or even zero, there was counting, which uses the natural numbers. We represent them as n equals 1, 2, 3, 4, 5, 6, etc. Some definitions include zero. This distinction depends on the context that the natural numbers are used in. Mathematics is consistent either way. Why do natural numbers matter? Because counting is structure. If you can match each object to a number without repetition, you've created a one-to-one correspondence. That's the essence of cardinality, comparing the sizes of sets, even infinite ones. Natural numbers obey two fundamental operations. They are addition and multiplication. Both operations are closed, commutative, and associative. In other words, a plus b equals b plus a. The sum of a and b plus c equals a plus the sum of b and c. Also, a times b equals b times a, and the product of a and b times c equals a times the product of b and c. But subtraction fails. 3 minus 5, for example, is not an element of the set of natural numbers. This failure gives rise to the integers. Natural numbers aren't enough to answer every question. But we're not talking about integers just yet. The entire set of natural numbers is generated by a single rule, the successor function. Start from 1 or from 0, and build forever. There is no largest natural number. This simplicity is formalized in the Peano axioms. 1. 0 is a natural number. 2. Every number has a successor. 3. No number has 0 as its successor. 4. If S of A equals S of B, then A equals B. 5. Induction. If a property holds for 0 and holds for n plus 1 whenever it holds for n, then it holds for all n's that are an element of natural numbers. This fifth axiom means that we are able to prove that something is true for all natural numbers. It is the backbone of most proofs in number theory and computer science. Also, natural numbers are well ordered. Every non-empty subset has a least element. This property lets us make firm, logical statements about how numbers behave, even into infinity. From natural numbers emerge divisibility and primes, modular arithmetic, combinatorics and partitions, algorithms and recursion, and so much more. Every branch of pure mathematics either begins here or passes through here. The natural numbers are not just how we count. They're how we begin to understand structure, logic, and the infinite.